Okay. I'm going to start by restating the Markov property that we started with, that ended with last time. And pretty much all the discussion today will be on properties of Markov chains and Markov processes. The terms are a little bit interchangeable when talking about discrete time processes, discrete space processes. But I'll just kind of ignore the difference for now. Anyway, we'll start the Markov property just to get you refreshed about it. We'll go to certain properties of Markov chains. Homogeneity, which means it doesn't change over time, or the probabilities don't change or are time independent. How to represent Markov chains. These equations called the Chapman Kolmogorov equations, which show how the probability of being in a state evolves over time. And then 4 important properties of chains: irreducibility, recurrence, periodicity, and ergodicity. And these are actually fairly, even though the names sound complicated, actually quite easy to understand. And that allows us to state the first theorem on how, what are the different kinds of Markov chains. This is like a taxonomy theorem. And then that allows us to compute what are called stationary probabilities. And then we'll get into the second theorem. And if I have time, I'll look into the mean residence time in a particular state. So to begin with, you have to realize what a Markov chain is, or a stochastic process is. It's just this, what we started out last time. You have a guy standing on a staircase who's kind of moving up and down. And what we're telling you are the rules by which the person can go up and down the staircase. What this translates to in a stochastic process is that we have a certain number of states. You know, we can draw these as circles like this. And we have certain rules that tell you how you transition from which state to which state, and what is the probability of transitioning, you know, staying in the same state or going to the other state, and so on. And when we talk about a stochastic process making a transition, what we're really saying is this, that we have some notion of time which will be discrete or continuous, and that the trajectory of this in terms of which state you're at which point in time is known until a certain point in time. And what you're computing really is which of these potential future next steps is that process taking. In other words, if we know the value of xi, which is the value assumed by the random variable xi at some at the ith point in time, is, let's say it's equal to 5, that means over here we're at 5, then we have some distribution of the future value of xi plus 1. Okay, we have some distribution over the set of possible states of xi plus 1. One of these is going to be assumed. One of these is going to be taken. And so what we say, when we say we move from state here to state here, what we're really saying is that the value of xi, let's say this was 5, so xi equals 5. So the xi is at this state. And what we're doing is we're saying, okay, the distribution of possible future states, let's say the state 6 and state 7, and we have some probability of staying in 5, going to 6, or going to 7. These are just the distributions of xi plus 1, 5, 6, and 7 over here. And we are essentially computing or determining the value assumed by the random variable xi plus 1 based on the probability distribution conditional on being xi equals 5. So conditional on being in this state, what are the future states possible? Okay, and that sort of is really what's being represented over here. When I go over representation in a little bit, it'll become a little bit more clear. I'm just kind of reviewing what we discussed in the last lecture. So before I move on, I want to make sure everybody understands what's going on here. So any questions about this at all? Okay. All right, you guys don't know what hit you. You just walked in the room and boom, I threw all of the stuff at you. And this is because I want you to read the notes and answer the questions. Okay, look at the questions, try to answer them. If you don't do it, the next lecture is going to be worse than this one. And the lecture after that, you will be hoping you never came to the class in the first place. Okay, so I want to hit you on the head with like a ton of bricks right now, just for your own good. Okay, and all right, so I'm going to go back to this, explain it one more time. Because if you don't get this, everything else over here is just complete garbage. You'll go and say, what the heck was ergodicity? Okay, is it synchronicity? No, that's a song by the Police. Ergodicity is a mixing property of Markov chains. Okay, someday I'm going to write the lyrics to ergodicity based on synchronicity, but not today. Okay, so to come back to this, The example was, we have a person on a staircase, and we are kind of going from stair to stair. And that is a concrete representation that you have in your mind. What I'm talking about here is we have a family of random variables x1, x2, etc., where this represents time, discrete time. Okay? What I'm also talked about, what we talked about last time was that we have a sample path, a trajectory, which is at the time I, we know what previous values happened because we know where everybody went. What we're going to do now is, based on the current value of the random variable, we're going to predict what the next one is going to be, and that prediction is based on a rule, and that rule is, what the description of the stochastic process is. It says if the value of xi is 5, then xi plus 1 is going to be something. All right? And so that's basically what's going on. So the moving from state to state is nothing more than choosing a particular next value of the random variable for the next time step. So xi, what is xi plus 1? Okay? Hopefully this is a little bit clearer. All right. Anybody want me to repeat this again one more time, or I can move on? Okay, so one problem I talked about last time was what happens when we have rules that make life complicated. So one way of making life complicated is the following, that says that, well, if I came 2, 5 from state 2, then I go here for sure, for example. But if I came 2, 5 from 1, then I'll go there for sure. Okay? In other words, the next value of xi depends on the past history. When you have this, life gets messy. It gets messy because you kind of don't know how to predict the future. You kind of have to keep track of all the past history. If you think about this as a Moore machine, okay, in a finite state machine, what you're saying is in a finite state machine, we have a very similar kind of thing. We have a particular state, and we have some transition probability. If some event comes in, we go to the next state. In a Moore machine, we have this nice property that when you have a particular state, you go to the next state based on some input. We don't need to keep track of a stack of previous states. Okay? If you keep track of a stack of previous states, what you really end up doing, is, in effect, is to have a very large, exponentially large number of states where you have to kind of break up all the past histories and spread it out. You need a place to sit. There's a chair here. Okay, I somehow need to find more space. Okay. All right, so we have the Markov property. It allows us to forget about the past. It's a memorylessness property, and we can write this like this. We say probability that xn plus 1 equals some value j is conditional on x n equals in, n minus 1 equals in minus 1, etc. This probability, which is the probability that you go to some state j in the next step, given the past history, is nothing more than pxn plus 1 equals j given xn equals in. In other words, I can ignore all of past history, and I'm going to get to the next state anyway. So these kinds of rules that tell you about the past are explicitly forbidden. Okay, and that's the Markov property, and that allows us to do many, many nice things. Okay, so that's basically what we're going to do. What is nice things? We're going to come over here. Generally speaking, if a stochastic process is not Markov, we're going to try very hard to make it Markov. Okay, there are some tricks you can use, which I won't get into, which can convert non-Markov chains into Markov chains, and there's something called embedded Markov chains and so on. I'm not going to go there, but from now on, you're going to assume that the Markov property holds. We're going to always assume that we can ignore past history. Okay, so this is just a quick revision of the Markov property. Now let me go into homogeneity. The easiest way to understand homogeneity is to look at an example of a non-homogeneous Markov chain. So let's say we have the same staircase like this, and we have somebody in stair number 5, and I'm going to tell the following rule. Okay, it says this: if you come, or maybe it's not, if you are at stair 5 at time 20 x21 equals, maybe I should say this, px21 equals 6 equals 1. And if you are at stair 5 at time 21, p x22 equals 6, x22 equals 4 equals 1. Okay, so what am I saying? Okay, so this is equivalent to x20 equals 5. I get this x21 equals 5. Okay. If we have the random variable x20, take the value 5, okay, because the trajectory says that at value time step 20 or 5, okay, that's fine. That gives me the value here. And then the first rule says that if you're at the means you're at time, the meaning of this x20 equals 5 is you're at stair 5 at time 20. And it's saying if it's time 20, you're going to go to step 6 for sure. Okay, p x21 equals 6 equals 1. Okay, for sure you're going to. However, if you get there at 21, you're going to go to 4. Okay, first question is this Markov? Okay, anybody want to? It's not okay. You're shaking your head. Why is it not Markov?
Just depending on the time it is taking decisions.
But we're saying it is not Markov because the decisions are time dependent. Okay. Okay, what is the Markov property? I just went over it. What is the Markov property?
It has nothing to do with the previous state, so it could be...
Right, so you're saying it could be Markov because there's nothing to the previous state. But I want to ask you the question in the back. Why is it not Markov?
This is not actually consistent, right?
It's not consistent. What do you mean it's not consistent? Consistent with what?
Time.
But the Markov property, which I erased right now, all it says is the probability that xn plus 1 equals j given sort of p xn equals in, etc., all that stuff is equal to p xn plus 1 equals j given p xn equals in. Right?
It doesn't depend on state, it depends on time too.
It depends on time too.
Yes.
I'm just asking you, is this Markov or not? So you're saying it's not Markov because it depends on time.
Yes.
Okay.
This seems like, to me, it's a certainty in a stochastic.
It's a stochastic, yeah.
It's no certainty, but if you said it equals to 1%, it seems like deterministic.
Okay, so you're saying it's not a stochastic process, it's actually a deterministic process. Every deterministic process is a degenerate case of a stochastic process, so that's not a valid reason. So, okay, forget about that. Yes, Ali.
Each state can be imagined as a pair.
Right.
First element is a state,
Right.
and second element is time.
Right.
And then the movement between the states depends only the current state.
Yeah.
So it's Markov.
You're giving me a reduction which is not unnecessary. Okay, so what you're saying is true, but you don't need it. Okay, let me see if somebody else. Yes, Omar.
It is Markov because the next state only depends on the last.
That's right. So Omar is saying it depends on the. So how many people agree with Omar? It is Markov. Okay, so well, now we can vote on mathematical theorems using, like election process for. Do you all believe that so and so should be proved true? If you all raise your hand, democracy wins. Unfortunately, this is not democracy. This is mathematics. Either it's true or it's false. Okay. Yes.
I thought the state was the probability distribution.
The state is not a probability distribution. The state is the domain over which the random variable chooses its values. Okay, the domain of the random variable is the state. All right. For example, in the staircase, you have 10 steps. The random variable is going to be one of those 10 steps. That is the set of states. Anybody else? Okay, so so this is Markov. The reason that it's Markov, and this is where people can get quite confused. That's why I kind of ask you is because we know if you're at stair 5 at this time, we know what the next step is. We never said in the Markov property that it's time independent. We just said that all I need to know is where you are. Okay, the past history can be forgotten. In fact, past history is forgotten over here. And these rules do not violate that. The rules are simply saying, if you look at the time which is given to you, and you look at where x20 is, I can tell you where x21 is. I can give you either a certainty, or I could have made it more complicated and said, this is 0.5, and p x21 equals 7 equals 0.5, for example. That would be a distribution over two states, and that would be stochastic. It wouldn't be deterministic, but it would be equally Markov. All right. The thing is, the random variable x21 depends on the past, only on the basis of the random variable x20, it turns out that if x21 equals 5, then x22 changes. So the fact that you got here at some particular time doesn't really matter. Okay, all of the past history can be compressed into just what is the current state. Okay, and that is the Markov property. Okay, so if you think this is not Markov, you really don't understand what Markov property is. That's why I want to make sure you get it. Okay. All right, I'm going to sort of stop again and say, okay, does everybody understand why these are Markov here? Anybody have any questions? By the way, you should realize there are no dumb questions, there are only dumb answers, okay? I'm 100% responsible for dumb answers, okay? So you can only ask smart questions against dumb answers. Yes?
On that note, Keshav, isn't time sort of a history in itself? Like
Time is not history. History means trajectory of previous states. Okay, so basically over here, xn equals in, xn minus 1 equals in minus 1, etc. That is your history. Okay, the time is not history, right? It just says, okay, the time now is this. Everybody knows time. There's no history per se.
you know your current time because you remember what your previous time was, and tick is one addition to your previous time.
Remember, there is no you here. There is no person. There's nothing going on. I'm just telling you that there's a stochastic process with I want to determine the value of, or the distribution of the random variable x21. I'm saying that if I know the time, which is given to me, okay, because x21, it's already there. 21 means time is 21, right? So I don't have to look anywhere for it. I just need to know the value of x20, the current state, to determine the distribution of x21. In this case, it's 0.5 of being in state 6 and 0.5 of being in state 7. Okay. Does that make sense? Okay. Anybody else? Somebody else had a question? Okay. It's very important to understand this. Okay. It's very important to understand this because it's quite easy to get confused because we have this, not just one random variable, we have a whole family of random variables. And not only are they random variables, these are random variables that are kind of acquiring their value step by step. At each time step, one more random variable becomes deterministic. Okay, that means you're adding history step by step. And all I'm saying is that over here, when I'm at this point, I can forget all the past history. All this has disappeared. I don't know anything about it. All I know is that here I am, x, in this case, x20 equals 5. And I know it's time 20. I can forget about the infinite past. And I know the distribution. I don't know the deterministic value. I know the distribution of x21, which is why I have p xn plus 1 equals j. I'm not saying you what xn plus 1 is. I only am telling you this is the distribution of xn plus 1. And then from that distribution, some actual value will be selected, okay, in accordance with that distribution. In accordance with the distribution. Okay? So, but that's, that's why I did probability first, so you guys know what the meaning is of in accordance with the distribution. Okay. Any other questions? Because I don't want to move past this point until everybody in this class is 100% confident of knowing a Markov process and recognizing it, okay, when they see it. Okay, so everybody got it here? All right? So, to repeat, we have a family of random variables indexed by time, and at one time step, we are sort of telling you the distribution over here of the random variable for the next time step, and the Markov property says, forget the past, we're just going to look at where you are, and in sort of more concrete terms, if I know that the person is at time state 5, I know the next distribution in a non-homogeneous Markov chain. In a non-homogeneous Markov chain, I need to know both the time and I need to know the step. Okay? So here what happens is, if I don't know the current time, I can't tell you the distribution. Okay? This is called non-homogeneity. But yet it's Markov. In a homogeneous Markov chain, I don't even need to know the time. Okay? In non-homogeneity, I can tell you the transition probability is represented as small p I j t. Okay? Let me make sure I use the right terminology over here. P I j, am I using small t? I can't remember the subscript or parenthesis. Right, anyway, so this is the transition probability of going from state I to state j at time t, and this is a non-homogeneous. In a homogeneous case, we simply have Pij. In other words, we don't care about time. Okay? So if I were to rephrase this question and say, is this Markov chain homogeneous? The answer is no, it's not homogeneous. Why? Because if you're at state 5 at time 20, it's different from being at state 5 at time 21. In a homogeneous Markov chain, you're always going to be taking the same next, the probabilities of the next values are always the same independent of time. Okay? And as I said, you got to be careful to distinguish between non-homogeneity and non-Markov. Okay, and this is a fairly common confusion that people have. Okay, any questions about this? Okay, so when we have a homogeneous Markov chain, life becomes a bit easier. And again, for the purpose of this class, we will be ignoring non-homogeneous Markov chains. Okay, and generally speaking, non-homogeneous Markov chains aren't that interesting anyway, okay, because it gets too complicated. You know, the whole process is very messy. We don't know what's going to happen. The whole purpose of the analysis in stochastic processes is to be able to predict the future with some accuracy. And if it gets very messy and complicated, we don't want to do it. So we're going to restrict the problem, make it easier and easier and easier. So we started out with the space of all possible stochastic processes. Now we're focusing on sort of discrete space, discrete time, Markov, so we don't need to worry about history, and now homogeneous, so we need to not even worry about time. Okay, we sort of time independent thing. So that's homogeneity. I'm going to talk about two representations. So, well, we have this Pij. We don't need to worry about time. So two obvious representations are this. We have a matrix, and we have basically Pij elements over here, and we call this cap P and bold in the text. Basically, the ijth element is the ith row, jth column is the transition probability of going from I to j. So in this case, it will be P00, P01, P0k, assuming there are 0n if you have n states. And this is Pn0, Pnn. So this matrix tells you the time independent probability of going from any state to any other state. And of course, there's the equivalent representation which looks like this. I have state 0, or let me just call it state I, I have state j, and then I draw an arc from I to j, and on it I write down Pij, and these are equivalent. And as you'll see, this is, of course, what we've been doing all along. And I've been drawing the staircase, I've been drawing circles. So here, this is the state. To be more precise, what is the state is the domain of the random variables x. Okay, that means this state is the value that can be taken by the random variable. Okay, and so transition from state I to state j is nothing more than saying that random variable xn, has equals I, and xn plus 1 has value j. Okay? Xn is I, and xn plus 1 has value j, and the probability that xn plus 1 equals j conditional on xn equals I is Pij, right? So we can just write that down like this. Pij equals probability xn plus 1 equals j given xn equals I. And as you can see right away, this is Markov, right? Because there's no past history, and you can see it's homogeneous because there's no dependence on time. Whereas in the non-homogeneous case, we'll just say Pijt equals x is equals probability xn plus 1. Sorry, I should be careful. Pijt probability plus 1 equals j conditional on xt equals I. Okay? And this is at that time only, Pijt. Okay, whereas here we have, for all n actually, you're getting this, whereas there it's dependent only at that particular time. So in other words, if we were to represent a non-homogeneous Markov chain using these two things, we would have this kind of straight transition diagram per time step. We would need this matrix per time step. We would need PT, but in a homogeneous case, we just have P. Okay? So one nice thing we get from the matrix P, and this will leave us an exercise for you to prove, is that P squared, which is just the matrix product of P with P, it will tell you the probability of going from a state to 2 states ahead. So P squared is nothing more than, it gives you the probability of xn plus 2 equals j given given xn equals I. Okay, I'm kind of not really writing the notation down properly, but you should think about what does P square mean, what does P cube mean, etc. And I think you'll understand a little bit more about the representation when you do this. And maybe I should just do an example. I'm going to do the example from here, and then we'll take a break, I think. So let's see. Let's say that we have the following situation. Let's say P11 equals 0.2, P12 equals 0.4, P13 equals 0.4. All right. Now, let me do that. P21 equals 1.0, P22 equals 0, P23 equals 0, P31 equals 3.5. Okay, so I've written down 9 transition probabilities, and these are time-independent state transition probabilities. You'll notice right away that the columns sum up to 1. Okay? Now, why is that? Somebody want to? Yes. Okay. Or anybody? Okay.
You have to go to another state.
That's right. So you got to go somewhere, or rather, I should say, again, the random variable xn plus 1 has to take on some value in the domain, right? Either 0, 1, or 2, or in this case 1, 2, or 3. So we know that the probability that the random variable acquires something, that means the trajectory extends forward is guaranteed, and so that always sums up to 1. The rows may not sum up to 1. Like this one, of course, is like 1.7, so it doesn't make sense. What is the matrix representation? Well, it's absolutely trivial. It's just writing it down like this, 0.4, 0.4, sorry. And because, well, I wrote the matrix the wrong way, right? It's really rows sum up to 1 in the matrix, the columns in this one, so don't get confused, despite my best efforts. And 0.5, 0.25. This is 1, 1, 1, 2, 1, 3, so that's why I'm writing it in that form. So this is P. And if we were to draw it, well, I only have 3 states, 1, 2, and 3. And then the transition probabilities is 0.2, 0.4, 0.4. So the sum of all the probabilities of leaving state 1 is 1. That's what these arcs add up to. And this is 1, this is 0, and this is 0. It means when you go to state 2, you always go to state 1 afterwards. And 3 has a self-loop at 0.25. At 0.25, it goes here. And it goes here at 0.5. And so this representation, or the matrix representation, are in fact complete representation of a homogeneous Markov chain. Okay? All right. Any questions about this? Yes?
Since this data diagram is very similar to the non-deterministic finite automata, so
Yes.
is there any relationship between NFA and this Markov chain?
So the question is, are non-deterministic finite state automata related to Markov chains? There is a relationship, but it's not necessarily easy to explain. But I can explain it in the following way. Assume that we can represent a program, okay, computer program, as a transition, a probabilistic transition, probabilistic finite state automata, non-deterministic finite state automata, right? Whereas I won't say non-deterministic, I should say probabilistic. Okay, that's where it comes in, because non-deterministic is different from probabilistic. Okay, I have a probabilistic finite state automaton which makes these paths, and I somehow figure out these probabilities. The execution of that program over time Okay, the execution of the program over time can be viewed as a particular sample path or a particular trajectory of a corresponding stochastic process. Okay, and if that execution is time independent, in other words, if you come to some statement number 10 and you go to statement number 12 always, so you go to 12, 11, whatever, if something then condition, right, and that condition probability always holds, and you go to these different states with some probability, then you can view the program execution as being a sample path through a stochastic process. And more precisely, what I talked about last time, a simulation where you're trying to simulate some state or some system, that simulation actually can be viewed as choosing a particular trajectory, okay, of the stochastic process, the corresponding stochastic process, and the end state of the simulation is essentially what xn, right, the last part. So there are some deep similarities here, but and so the theory of stochastic processes has much to tell us about how to do good simulations. Okay, but I won't get into that over here very much. But yeah, clearly there is some relationship, and also I should point out that the finite state automata, which we studied in discrete math, are sort of influenced by and related to Markov chains. Okay, but it gets it's a bit more complex than that. But just at a high level, yeah. Any other questions? Yes.
So, can't you represent time as a just initial dimension on this condition matrix?
Yes, you could. I just said you can have PT, right? You could have essentially one matrix per time, and that would give you a third dimension, if you will. Yes, you could do that. Except that now we kind of have to follow this path through time, so we kind of go through time in that fashion. Yes. You can do it. Representation is not hard. Analysis is hard, okay, because you have to kind of keep track of what time it is to know what the state it is, or what the transition probabilities are. Yeah. But yes, it would be easy to do. Any other questions over here? Okay, let me stop here, and then we'll continue with m-step probabilities. Okay, so I'm going to leave equations. These equations are actually, the names are longer than how, it's very, very simple equations, just sound complicated. And so, if somebody asks you, what did you do in grad school, and you want to, kind of impress them, you can say, I studied the Chapman Kolmogorov equations, and say, ooh. But not most people just say, oh, that's a waste of time. All right. Anyway, my kids are impressed, but then they're 10 and 12 years old. They're impressed with anything with long names. So we know what Pij is. Pij is basically probability of going from state I to state j. Okay, I'm going to define a new term, which is the Pmij. By the way, the terminology I'm using is straight out of Kleinrock Volume 1, so if you want to look it up, that's the kind of the Bible of queuing theory. This one is defined like this. It's probability that xn plus m equals j, conditional on xn equals I. Okay? That's it. It basically says I get from state I to state j after m steps. So if m is 1, then of course we get our standard. So Pij, it can be represented as Pij 1. Okay? That's just the same thing. So it says that if I am at time step n, I am at state I, what is the probability that at time step n plus m, I'm at state j? And this is very related to the previous question I asked you. How do you get Pn plus 2, which is the square of that P matrix? And this can be shown to be, and it's very easy to show, as nothing more than the sum over k, Pik, m minus 1, Pkj. All right? And m is... Okay? Well, what are we saying over here? We're saying that to go from state I to state j after m steps, I'm going to go from I to some intermediate state k in m minus 1 steps, and then I'm going to do this one-step transition from k to j, which of course is the same as pkj. All right? So we can draw it like this. We have I, we have some m, and we have some j. And so we're going to m to j in pmj, and then somehow we get from here in m minus 1 steps. Okay? And now we can ask ourselves, the first question is, why can we multiply these two things like this? Okay, sorry?
Because you're adding the probability.
That's right. These are independent events, right? The probability of getting from I to M, the probability from M to J are independent events because there's no history. Right? If there was history, I'd be in trouble, but there's no history, it's Markov. So this product can be there because independent events. Similarly, if I take some intermediate, if I take all the different ways of getting to, I'm sorry, this is not M over here, this is K over here. If I get to all the different Ks, somehow I'm getting to that K, and then this should be Kj. Those are again independent, okay? And I can add them up. So independence is, and memorylessness allow me to write this equation down. Okay, so this equation is called a Chapman-Kolmogorov equation. Okay, so that's why I said its name is longer than what it does. And I can write it a different way. I can write it like this. I can say I can go from I to one of a set of Ks like this, and then in some path I'm going to get to J. So how would you write this? It's going to be equal to sum over K, P, I, K, P, K, J, M minus 1. Two, 3, etc. Okay? So here I'm saying you go m minus 1 steps and you make one last step over here. And this one is called the forward or the backward. I can never remember. I think these are called the forward. Is it forward? One of these is called forward, one is called backward. It doesn't matter. They add up. They're basically two different ways of saying the same thing. I'll figure. I can never remember which way is which. It doesn't really matter. Okay, just use two different ways of doing it. So these equations, because actually what we have is we have a family of equations because it's true for all I and all j and all m, right? For all I, all j, all m, I can write down these equations. So I get a large number of equations, and these are called the Chapman-Kolmogorov equations, and they just fall right out of the Markov property and the homogeneity property. Okay, now there are, in fact, you can write down the Chapman-Kolmogorov equations also for time-dependent or non-homogeneous Markov chains, and you can figure it out. It's not particularly hard to do, but I'm not going to write it over here. You just have to introduce time and kind of mess around with notation a little bit, but I'm not going to show that over here. This is the time-independent Chapman-Kolmogorov equations. Any questions about this? Easy. Okay. If you understand Markov, this is easy. So I'm just going to leave it there. Okay, let's start kind of plowing through that list a bit fast because it's really quite easy. I'm going to use a representation which is the state transition diagram because it's easy to write down and draw. So consider the following Markov chain like this. It's an infinite Markov chain, and what I'm doing is let me draw one more. If I'm an even state, I can go to only an even state. And if I'm an odd state, I can go only to an odd state. Okay? That's a Markov chain where from even state I can go to even states, and odd state I go to odd state. So obviously, in such a Markov chain, if I'm an even state, I will never enter an odd state. And if I'm an odd state, I'll never enter an even state. So such a Markov chain is called reducible. And conversely, if every state can be reached from every other state, okay, so P, I, J, M not equal to 0 for some M, and for all I, for all j, that means I can get to from I to j using some number of steps. I don't care how many. Okay? Then it's called irreducible. And the reason why it's called reducible is like this. I can take this chain and kind of spread it apart, and then I get two different chains. Okay? They don't even talk to each other. Okay? These two chains, so I can reduce this Markov chain into two separate chains which once you enter one chain, you're never going to go to the other chain. Okay, and so we can reduce it in some sense, whereas it's irreducible, we cannot. Yeah.
Suppose we have 3 states and they are like connected in cycle.
Yeah.
In deterministic process.
Yeah.
Do we have such an M?
Yeah, because I can go. I mean, there's some probability of going from I to j for all j, right? In m steps, because I can take 1 step or 2 steps or 3 steps. What you're saying is a ring, right? Let's say a 4 ring. Okay, I can go from here to here in 1 step, here to here in 2 steps, here to here in 3 steps, and back in 4 steps.
And then it probably means that we need to change this for all I, j, there exists some.
That exists m. Okay, I probably should say that. There exists m such that.
I'm saying exists m should be after all I, all j.
Yeah. Am I getting the existential the wrong way? There exists m such that. Okay, let me just state it in words. Irreducible. I don't want to come up with the existential and for all quantifiers in real time. Every state is reachable from every other state. Where reachability is in the graph theoretic sense. Okay, so you can figure it out. Okay. Most likely it is, but I don't want to mess up the logic is something you can't do in real time. At least I can't do in real time, and I don't want to mess up the existential and the universal quantifiers in a way that confuses you. I can state it in English, and you can figure out the logic. It's not a big deal. Every state is reachable for every other state. In this case, it's not true. Therefore, it's not reducible. Okay, it is not irreducible. It is in fact reducible. It's okay. And we need this because we just want to avoid some degenerate cases. Okay, and we use the term irreducibility when we talk about ergodicity. So this is really very, very straightforward. I don't want to waste any more time on that. Let's talk about recurrence. So recurrence. Let's go back to the staircase. So this guy is staying on step 5, stair 5, and he asks the question, will he ever come back to stair 5? Ever? Okay. Could be 2 answers. No, because it's an infinite staircase and he keeps climbing up. So once he goes to stair 5, just keeps going, never stops. Okay. Then that state is not recurrent. Okay. However, if there exists some m, okay, there we go again. There exists some m so that you're going to be coming back to that stair again in the future. There's a non-zero probability that you're going to come back to that state in the future, then we call that state recurrent. So it just says that some state, so recurrence of a state j means that after entering j, okay, so we're conditional entering j in the first place. If you never enter j, then it's like it doesn't matter because you never entered that state. But after entering j, non-zero probability of re-entering j. Okay, and that means recurrence of state j. All right, and that's basically it. Now, generally speaking, if you have finite irreducible Markov chain, it's going to be recurrent as well. Okay, because it's finite. We're not going to go off into the future, and it's every state can be reached from every other state. So obviously, going to come back somehow, right? And that's why finiteness of a Markov chain immediately gives us recurrence. Okay, we'll see that more formally in a minute. Okay, does everybody get recurrent? Now, yeah. We will re-enter J with probability 1. Let me see. Okay. I think it's... Yeah, we will. I'm sorry, you're saying it should be not non-zero, but it should be probability of re-entering is. Yeah, you will definitely recur. Yeah. Right. It should, you will. Yeah, I'm sorry. Yeah, I got the. I flipped it around. You will say that. Yeah. J is 1. Okay. Right. Non-zero probability versus you will surely re-enter. Let me see. I got it.
There is if the probability of returning to J is not 1, is for example some number between 0 and 1, there is a positive probability that you won't return to J.
Yes. Right. So the reason I'm thinking about it is because some sample paths will not return to J. Okay. I'm just thinking: are we constrained that every sample path must return to J, or are we talking about? So if you're saying probability is 1, that means every sample path must return. I don't.
It's conditioned on being at state J.
Yeah. I don't believe that's true. Okay. Let me check on that, because my understanding of recurrence is that there is a non-zero probability. Let me get back to you on that, because I don't want to give a wrong answer here. Okay. Yeah, because we can think of sample paths for a recurrent Markov chain which actually do not go back to that particular chain. Okay. For finite sample paths. It's possible, I won't get back to it. Okay. So the probability should be non-zero for sure. Is the probability 1 of re-entering? I have to think about that. Okay. Let me put that on hold for now. We'll talk about a little bit more interesting part of recurrence, which is the notion of recurrent null and recurrent non-null. So what we can think of is, if we have a recurrent state, we can look at the expected recurrence period. Yes?
Is your definition of recurrence, why is it necessary that if it's finite, you have to come back to the same place?
If it's a finite chain and I have a long sample path, right, with some non-zero probability, I have to come back to that, because remember, I'm looking at distributions of the future. So there is some sample path that's going to get me there. And if some sample path gets me there, okay, because I have an infinite walk through a finite set of states, right?
What if it's like all of the states are going to one guy with probability 1, and you start at somebody, you don't reach there, and then just keep looking back at that state?
Yeah. So if you're going to have kind of these degenerate thing, then it's not irreducible anymore. It becomes irreducible, because I can't reach from every state to every other state, right? So finite, irreducible Markov chains will have recurrence, will be recurrent. Okay, your case would be reducible, right? Because you all go to this one guy, then I can't go back. Then it's not. It becomes irreducible. So it becomes reducible. Okay. All right. So as long as you can reach every state from every other state, if you have an infinite sample path, I'm going to hit some sample finite state. This is like a pigeonhole principle kind of deal, right? I'm waving my hands over here, but that's the essence of the mathematical proof. It's not intuitively correct. Okay, so we can talk about the following thing, which is the expected recurrence period. Okay, let's use the following notation. F J n means that that's the probability of the first return to state J is after n steps. So probability first return to state J, which is the subscript over here, is after n steps. Okay? How do we compute Fjn? Well, we can think about it like this, right? Let's look at the state over here. If I leave state 1, I'm going to come back to state 1 with probability 0.2, and Fj1 is just 0.2, right? How about 2 steps? Okay? To get 2 steps, I can take this twice, right? Or I can go here and come back, or I can go here and come back. So I have 3 different ways of re-entering state 2 after 2 steps. Like each of these independent events, I can kind of take the product and add it up. How about 3 steps? Well, same thing. I can do once and then this, or whatever, right? This exponential number of paths I'm going to keep trying. However, in theory, certainly, it's computable, right? You can just compute these things. It's a long computation, but we can define this, okay, what fjn is for each state j. And then we can compute just this. We can compute sum n equals 1 to infinity n f I n. Okay, that means that we are recurring, this is just the expectation, okay, over the infinite sum. This is expectation over here. I need to make the j a bit smaller. So this one over here is just the expectation of how many steps I'm going to take to re-enter that state. Okay? If this expectation is infinity, all right, then we call it recurrent null. Okay, and if expectation is finite, we call it recurrent non-null. So this one, if it's finite, it's called recurrent non-null. And if it's infinite, recurrent null. And I should point out that a recurrent null is again like a pathological case. You constructed this bizarre chain so that these expectations of are such that these the expectation turn out to be infinity. Okay, there's a lot of mass on the right hand side, so to speak, and it takes a fair amount of work to make it recurrent null, as far as I know. As far as we're concerned, as far as if you're worried about engineering or most analysis, it's pretty much guaranteed it's going to be recurrent non-null. Okay, so if your recurrence is going to be, expectation is certainly going to be bounded, finite, in which case it's a recurrent non-null chain. Okay. All right, I'm going to throw one more definition at you, and then we can finally talk about ergodicity. So again, it's let me show you this following chain over here. Okay, so in this chain over here, and let's say the transition probabilities are all 1, okay, if I have this kind of thing, what's going to happen is I'm going basically state change is 1, 2, 3, 1, 2, 3, 1, 2, 3. It's deterministic, okay, and in fact, it's what's called periodic, okay, because I'm going to be going through these states periodically, all right, and however, if I put a self loop over here, just one self loop, if I do one self loop over here, it becomes, I can't determine the period anymore, because I could, I could have a cycle of 3, a cycle of 4, one cycle of, basically I cannot tell you that there is a period which is greater than 1, right, which is the least common denominator of my visit times to a particular state, all right, because I just have this one self loop. But if I take away the self loop, then what I get is what's called a periodic Markov chain, and I can define that more precisely. Given a recurrent state j, so it has to be recurrent, otherwise there's no point discussing it. Suppose only way to return is to take r to r, so kr steps, r greater than 2, okay, then state j is periodic with period r. Okay, that's the definition. Again, it's pretty intuitive. Okay, I cannot come back to that state other than as a multiple of some number r, which is clearly true here, r equals 3. But as I mentioned, if you put a self loop, okay. So when we study Markov chains, we don't like periodic chains. Very simple. We don't like periodic chains because all the properties of interest become periodic. Okay. So if you want to know what state I'm in, you kind of have to know, well, what time is it now? Is it this or this or this? And everything kind of changes based on that. And it's not like the time is important per se, but what phase you're in, because really these things keep changing in this. So intuitively, what's going on in a periodic chain is that it's not mixing very well. Things are kind of going through this phase. I can think of a ring with n states. I'm going through state 1, state 2, state 3, kind of going in a ring, like a traffic light changing from red, green, yellow, whatever, round and round and round. Everything kind of depends on what the current state is, and we lose this chaotic property. Okay, what we want, in some sense, maybe I should say more precisely, what we can analyze best are those chains where everything is mixing around, okay, so that we lose the dependence on the initial state, because we don't know the initial state. We don't know the initial state. What we want to happen is that we enter at some state, things chug along, and after a while, we don't really know where we started from. Okay, we're going to be in what we call steady state. Okay, and that's called the stationary distribution, and we'll study that in just like a few minutes. But I'm just trying to point out that the fundamental analysis of these chains becomes easier if we have what's called ergodicity, okay, which is our next topic I'm going to talk about. And ergodicity is broken. Ergodicity is broken if we have some bad conditions. One bad condition is we can't get from any state to some other. The two states says that they can't reach each other. Okay, if you can't reach each other, then I can't tell you this. There's dependence on the initial conditions. For example, if I start an even state, I'm going to end up in an even state. I can't tell you anything else. So I don't like that. So I'll say, okay, I don't want it to be like that. So I'll say the chain has to be irreducible. Okay, just a minute. The second thing that's kind of bad is that I have some kind of phase change going on. So I go from phase to phase to phase, described in this fashion. Again, I don't want that. So I'll say I want it to be aperiodic. The third thing that happens is I go to a state and never come back. I come to a state and kind of I go right past it. I don't come back again. So I want it to be recurrent. And in fact, I want it to be recurrent non-null. Okay? So if these conditions hold, then intuitively I have a system where once we enter it, we're going to come back to some state. We're going to reach every state from every other state, and there isn't some kind of period. Okay, I cannot identify any particular period that gets it, and these conditions promote mixing. These conditions promote forgetting of past history. Okay, forgetting of what state you started from, and this is what's called ergodicity. Okay, so I'll take a short break, and I'll give you sort of a more mathematical definition of ergodicity, but there's a question at the back. Again, it depends on the kind of chain. Okay, for finite and recurrent chains, okay, if any state is aperiodic, then all states are aperiodic. And again, we'll come to that in just like after the break. But the short answer is the first fundamental theorem, which is over here, is that if any state is periodic, all states are periodic. Okay, for recurrent, non-null, homogeneous Markov chains. Okay. All right, let's take a short break here, and I'm going to still leave this up over here because I'm going to solve this one over here. But
recurrence expectation will be finite, because if that for that the probability should become 0 after some.
Or tail off pretty fast, exponentially fast, or something like that. Yeah, we need that summation to sum up to basically that series has to be convergent.
Yeah.
Okay.
So
you take this is a convergent series, for example. You can show that this series is convergent. This is a recurrent non-null Markov chain. Okay, just hold on to your thought, because once you do the first theorem, it will all become clear. Okay. It depends how you define the rules, right?
Yeah, but like normal, when you just in each time step, there's like probability 1/2 up and probability 1/2 down.
Right. If you look at the probability 1/2 up, 1/2 down, we can draw the Markov chain like this. Okay? Right? And if you define that you can never stay on this on the same step, you have to go up or you have to go down, and it is if it's going to be infinite, I don't know if it's infinite here, maybe finite is probably enough, then you'll have a period of 2 in this case. You're going to be the only basically going to come, yeah, if you don't have any self loops, then it becomes periodic with period 2. Yeah. Which you don't like. So that's why we have some probability of staying on the same step. But yeah, this would be a period. Okay. Any other questions? Yes.
Because you can keep going to a step, then back, then 2 forward, then 1 back. You won't have a period.
Well, so period is going to be, so I'm going to do 2 or 4 or 6 or 8, and then we're going to have 3.
So if you have another state, you have 4.
But to get back to the state, remember, the period is for a recurrent state that I get back with 2R. R is in this case 2. 2R, 3R, 4R, etc., right? So maybe I should say, yeah, so I can either take 2 steps or 4 steps or 6 steps, etc. So these are all multiples of 2. It's greater than 1, so it's periodic with period 2. Any other questions about this? So at this stage, you're kind of probably wondering, why are we going through all these fairly exotic definitions? Again, I'm trying to motivate that by saying what we really want is ergodicity, okay? And once you get ergodicity, life is great, but we need to get there. So right now, what we're doing is, you're kind of looking at all the pathological cases and saying, okay, that's a pathological case, that's a pathological case, and then the theorems will tell you if we ignore the pathological cases, then life is great. And it turns out that all the analysis that we'll start doing, probably in the next few lectures, will be assuming the pathologies don't exist. Okay, maybe you can pause this. To motivate ergodicity, and let me do that. So I'll first just define what ergodicity is, because the definition is actually pretty straightforward. Ergodicity means that a chain is, I should say, state J is ergodic if recurrent, non-null. That means you get back to it with the expected period less than infinity, and aperiodic. Okay, that's it. That's just a shorthand for saying that it's recurrent, non-null, and aperiodic. Okay, and we can kind of see that if a chain is irreducible, okay, or reducible, then it cannot be recurrent, because I can't reach every state from every state. I'm not going to come back to that state necessarily. Anyway, so this is the definition of ergodicity, and a Markov chain is ergodic if all the states are ergodic. Okay, and it can be shown that there's a theorem which is a sort of maybe more like a lemma, which says that a finite, irreducible aperiodic Markov chain is ergodic. Okay. So if it's finite, that means there are infinite number of states. It's irreducible. I can get from every state to every other state. It's aperiodic, and the quick hack is one self-loop anywhere. One self-loop. It's ergodic. All right. So by inspection, I can just look at a chain and say, "Yep, it's ergodic." Is this ergodic? Well, it's finite. Okay, that's great. What's the second one? It's aperiodic. Well, I have one self-loop, and it's irreducible. Yeah, I can get from every state to every other state. This is ergodic. Okay, so this is a nice little theorem to have in your pocket, and you'll probably use it often. Okay, and it's just something to know. And so what we're basically showing is that these two things are equivalent. You can have finiteness, irreducible, aperiodic. So if you take out the aperiodic part from these two, cancel these out, finite, irreducible means it's recurrent, non-null. Okay, and I think that was one of the questions that you asked, Robin. And so that's what you get out of here. It's finite and irreducible, then I can get recurrent, non-null out of it for free. And that's basically this intuitive understanding that infinite paths through finite spaces are going to be having expectations, non-infinite expectations of recurrence. Okay, so this is just a definition, and ergodicity actually turns up in many, many different places. Okay, and again, intuitively what's going on is that we've thrown away all the pathologies. One pathology is that it's periodic. Okay, then we have this phase dependency. We got that out of the way. And we also say that it's recurrent non-null, or maybe we say in this case it's irreducible, okay, and finite. Either case, what happens is that we find that we have this very nice property. No matter where we start from, okay, in the chain, after a period of time, so you start the chain at time 0, okay, and now the time is, okay, let's say it's time 50 or 60. I'm going to ask you, what is the probability of being in state 10, okay? So I'm asking you, what's the probability of being state 10? Well, let's think about that for a second. Actually, I can just do this chain over here. If you start in this state over here, okay, and I ask you what is the probability of being in state 1 at time step 1. So state time 0, you're here. At time step 1, what's the probability in being state 1? Well, it's 0.2, all right? I know that just from the self-loop. What's the probability of being in state 2? Okay, that's 0.4, and this probability of being state 3 is also 0.4, so I get those from this chain over here. Okay, but it's conditional on being 1. If I started over here, what's the probability of being in state 1? Okay, well, it's 1, but the probability of being state 3 is 0, right? So there is, if you start at time 0, at the next time step, the next immediate time step, there is dependency, all right? However, if I go sufficiently far into the future and you just pick a time and you say, okay, what's the probability you're in state 1 right now? If the chain is ergodic, I can tell you the answer. I can tell you that with this probability you're in state 1, with this probability in state 2, and this probability in state 3, it doesn't matter where you started. Okay, this is what's called the memorylessness or mixing property of ergodic chains. Okay, and this property becomes very, very useful. All right. So, so this other thing you can do is to say, we can do the following thing. We can say, let's say in this state I have some quantity takes some value. Okay, for example, in this state, you know, whatever, the packet arrival rate is something. In this state, the packet arrival rate is something else. In this state, the packet arrival rate is some other value. Okay, so I have a 3-state Markov chain. I want to ask you, what is the mean packet arrival rate? Okay, it turns out that if it's ergodic, I can just multiply the long-term probability of being in this state with the packet arrival rate in this state and just sum it up, and that in fact will be the mean packet arrival rate. Moreover, any sample path will converge to that mean very fast. Okay, we won't have these funny situations where the sample path deviates from the expected path, you know, from the mean path very far away. Things will kind of get mixed in pretty well. Okay, and I'm being vague here, deliberately vague here, because the study of ergodic Markov chains or ergodicity in general is very complex. You can find actually books on ergodicity, and there are many, many kind of interesting things going on under the covers. But you know, what I want you to get is this intuitive understanding that ergodicity means good mixing. Okay, less dependence on the initial state. Okay, that's basically all you really need to know. So we now have enough terminology to prove the first theorem, or state the first theorem. I'm now going to prove it. What's the first theorem? Okay, and it basically states that, I'll just write down the statement and then draw a figure explaining it. The states of an irreducible Markov chain are either all transient all recurrent null or all recurrent non-null. Also, okay, if any state is periodic, with period R, all states are periodic. Okay, so this is like a all or none kind of theorem. Okay, so I look at a state and I say, okay, if it's irreducible, okay, that's all we care about. We just need irreducibility. That means we can't separate them out. So it's very kind of broad statement. Okay, as long as I can reach every state from every other state, I can immediately categorize things into three main categories: 1, 2, and 3. The first one is transient. Okay, so you go to a state and you never re-enter it again. You just never re-enter it again. That's called transient state. And okay, that's what's going to happen. The second one is that all the states are recurrent null. Okay, which means that you're going to recur, but the expected recurrent period is infinite. Okay, expectation is infinite, or they're going to be all recurrent non-null. So these two are essentially, as far as I'm concerned, I'll call them pathological. Okay, I mean they're mathematically interesting, but from any engineering approach, these are just pathological states. You don't want to go there. Okay, if they're all recurrent non-null, then we get these two cases: either they're periodic, okay, in which case your period R, or they are aperiodic. Okay, so if any state is periodic, then all states are periodic. Okay, and so we want everything to be aperiodic, because if it's aperiodic, what do we get? We have, it's irreducible, okay, and it's aperiodic, and if it's finite or a recurrent non-null, either one, you basically get ergodicity. So if you get this one, I should put it else ergodic. Okay, so this theorem allows us to say, look, I'm just going to look at this chain, and I'm going to say, okay, well, it's all transient. If it's not irreducible, well, who cares anyway? If it is irreducible, let's say if it's transient. If it's recurrent, non-null, etc. I just want to pop out over here at ergodic, okay, because that's when life becomes good. Yeah.
And what's the definition for transient?
Transient means that you never return to the state. A state is transient if the probability of re-entering it is 0. So once you go to state J, you never come back to state J ever again. That's a transient state.
Yeah, but then that's there inside the definition of irreducibility, right?
Right. Wait a second. No. So okay. So let me think about this. You're saying, can we have a irreducible chain that has transient states? Right? That's what you're saying. I believe the answer is yes. I don't know what it looks like. Okay. I'm sorry, what?
If it is infinite, then it's possible.
It's infinite, it's possible.
It's the straight line chain. Infinite straight line.
Yeah, but we have to be able to come back to previous states. Possibility should exist that we can't come back, otherwise it's not irreducible. Otherwise we can't go from every state to every other state. Okay, this one is a bit tricky, and it has to do with the sample path thing that I was talking to Ali about. Are we saying that every sample path returns, or some sample path returns? Okay, so let me find an example for you. Okay, so we want an example of an irreducible transient. Okay, let me get back to you on that. Okay, because these are all different kinds of monsters, and okay, and I haven't seen this one yet, but and it's not important, right? It's like, yeah, sure, there's a monster. Okay, all right. So this is the first theorem, and all we really want is actually this theorem is more useful in my opinion than that one. But anyway, I'm following Kleinrock here, who basically says this is the first fundamental theorem. All right, fine. I'm now going to introduce a new, running low on time. Okay, I'm going to introduce a new definition, and then I have a feeling I'm going to run out of time. Okay, so let me just introduce the notion of stationary probabilities. We want to do the second theorem today, which means, okay. So, stationary probabilities. So intuitively, a stationary probability means the following. I have a stochastic process, and it's doing what it's doing, going from state to state to state. It's like a guy, as I said, a person going up and down these stairs, right? Going up and down these stairs. I want to ask the following question. At a random point in time, I just sample it. So let's say the staircase is behind a door, and I have a box which has it has a piece of uranium, and when the uranium decays, I get a spot on my screen, so that's an exponentially distributed random process. It's very random. When I get a blip on the screen, I open the door and I see the person. They're on some stair. Which stair are they at? Okay, I want to basically find that out, and now I want to find out the expectation of being on each step. Okay, this is what you can think of as being the stationary probability distribution. Okay, now remember that there is some state dependence even in an ergodic Markov chain. Okay, there's some dependence on initial conditions, but the stationary probability is in the long run. In the long run, if I just get a snapshot, where is this person going to be? Okay, that's the stationary probability. Okay, so in a homogeneous chain, we know that the state transition probabilities are homogeneous. Okay, I mean, are time independent. I can go from some state to some state, doesn't matter on the time. So there's an intuitive expectation that, in fact, assuming that it's not pathological, assuming it's homogeneous and ergodic, I will in fact be able to find this long-term probability of being in any state. Okay, there is going to be such a probability. In fact, that intuition is true. All right, so we denote, so let pi j n, okay, denote the probability p x n equals j. It's just notation. I'm saying what's the probability that the random variable x, okay, xn in that family is j. I'll just call that pi jn. It's just actually the same thing as xjn. The initial distribution, initial value is pi j0, okay, and we'll call this as pj. Okay, so I'm removing the 0 over here. We'll say that pj is also the stationary probability of the Markov chain if okay. So what am I saying? I'm saying if I start with pj in this very special configuration, okay, this very special distribution, then we can think of that as being the fixed point, okay, of the system. So the system goes one more step, and gosh, the probabilities remain the same. Okay, so in other words, the probability of being, if you start with pi j 0 equals pj, then pi j n stays at pj. Okay, it's exactly a fixed point of that particular transition function. Okay, so that is the definition of a stationary probability. I didn't tell you how we determine pj, right? I'm not telling you how we get there. I'm just saying that there exists a distribution, okay, which is p0, p1, p2, etc., such that if we make the initial value of probabilities of being in each state being pj, then it's always going to stay pj. So is it even possible? Can we even do this? Well, let's look at this following example over here. I just want to do a very simple two-state chain. All right, and let's just go like this. So it's 0.75, and this is 0.75. In fact, it's a very simple symmetric chain, and then the heart of this is that it's symmetric, and you can figure out why symmetric is important. All right, I'm going to tell you the stationary probability distribution, which is p0 equals 0.5 and p1 equals 0.5. Okay, it means at time 0, you have probability of being here 0.5, probability of being here 0.5. Okay, let's say that this is the case. Let's compute. Okay, so I have basically pi j0, pi 1 0 equals 0.5, and pi 1 0 equals, pi 2 0 equals 0.5. Thank you. So what is pi 1 1? Well, I'm going to stay here in this state with 0.25, start with 0.5, so it's 0.5 times 0.25 plus, I'm going to move to, I'm going to come from here to here with 0.75, so that's 0.5 of being here times 0.75, well, that's just 0.5. And just symmetrically, pi 2 equals 0.5 also. And obviously, I can see that pi n, just repeating this argument, pi 1 n equals pi 2 n equals 0.5. Okay, so I'm just showing you that such a thing exists, that a stationary probability distribution in fact exists. The distribution in this case is simply 0.5, 0.5. Okay, so with this probability, if I define this to be the initial value, it will stay there. If I define something else, okay, well, I don't know. I'm not telling you anything else, but anything else. I'm just telling you, if this is the case, this is going to remain over here. So at least existence is there. Okay, yes?
It's clear that every Markov chain has a stationary probability, but is it unique?
Is the stationary probability distribution unique? Second theorem coming up next time. Answer is yes. We actually have if it's ergodic. Ergodicity in the second theorem gives us essentially a very, very simple linear system to solve, which gives us the stationary probabilities kind of without even thinking about it.
Because stationary probability exists even for just Markov chains without any of the properties. That's the eigenvector of the matrix.
Yes, but life is much easier. The determining the stationary probability as a computational process is very trivial when you have ergodicity. If you don't have ergodicity, we have time dependency, etc., then it gets messy. Can be messy. Okay.
Isn't it still the eigenvector? You have the matrix, it is n cross, and you just need the eigenvector corresponding eigenvalue 1.
If it's homogeneity, if it's homogeneous, I'm sorry. If it's homogeneous and for the eigenvector to exist, right, we need existence, right? We need to look at to make sure it's reducible, for example. Okay, I think that the existence of eigenvectors is probably going to reduce to ergodicity. I don't know, I have to check on that, but I think, eigenvectors are not guaranteed to exist, right? You can think of the rotation matrix, which has no eigenvector, for example.
You mean the real? I mean, eigenvectors might have negative entries. Okay.
Right. Yeah.
So for a stochastic matrix, that where the rows sum to 1,
right.
there's the Perron-Frobenius theorem which guarantees that there will be an eigenvector which will have all non-negative entries and the eigenvalue will be 1.
Yeah. Okay, let's take this offline because I really want to finish. But the short answer over here is that for the case of interest, which is finite Markov chains which are ergodic, we can compute the stationary probability. All I want to focus on right now actually is something even simpler. I'm just defining stationary probability, okay, over here. And all I'm saying is that it has intuitive meaning. The intuitive meaning is that if I just take a sample of where the chain is, or to be more precise, what is the value, what's the probability, okay, that Pxn equals j for each j, okay? If I want to compute this distribution, I'm saying that this value, which is nothing more than pi jn, okay, the limiting value of pi jn is in fact going to be the stationary probability distribution, okay? And in fact, I can give you a computational method that says if by magic I tell you the initial value to be this, and I chuck through this and I come back with the same thing, then I'm just giving you sort of this plug and chug approach to verify that what I gave you was in fact a stationary probability distribution. I haven't told you how to find it. I'm just telling you that it can be done. And then the second theorem says, okay, how do we find these guys? So if I give you something like this, and as I find the stationary probability distribution, how do you find it? I mean, it's not obvious just looking at it what it is. If you look at this, you say it's symmetric. Yeah, I think 0.5 is going to work, and in fact it works. Okay, and look at this, it's not symmetric. How do we find the value? And that's what's going to be the second theorem. All right, let me stop here, and I'm going to urge you to review the material. I've covered up to page 14. And please try the exercises. It's very, very important that you try the exercises. And we'll continue on Tuesday.